Our fifth installment from chapter 8 is another big one. Now that we've discussed delocalized electrons and how they affect molecules as a whole, we can dive into discussing how this affects the products of a reaction, which is what this video is all about. We've seen differences in carbocation stability, which kind of brings our attention to the fact that, okay, electron delocalization is important. It outweighs some of our previous rules, right? Like right here, I might predict as a product of this reaction, all right, that would have been a secondary carbocation on this alkyl chain. So that would be the primary product. Well, no, right? Because it goes via a benzylic carbocation, even though they're both secondary, right? So earlier, if we're just using our chapter 5 and 6 rules, we would have said that that's a 50-50 mix based on Markovnikov's rule. Okay? So be on the lookout for that in the future, right? If it's an older reaction, consider your allyl carbocations, consider your benzyl carbocations, right? Because that's going to tell you what product will predominate based on the stability of the intermediates. Okay? Now, one other thing I want to draw your attention to before we go too far, this is a molecule of HBr reacting with this pi bond. Okay? Note that our traditional chapter 6-7 reactions don't occur with the double bonds in benzene, okay? Because benzene itself is too stable due to the aromaticity we'll talk about in a later video, right? But you wouldn't take HBr and react it with any of these pi bonds. Anything in a chain or a side chain rather is fair game, however. So keep that in mind, right? One minor thing to pay attention to, but really what this video is all about is reactions of dienes, okay? Because electron delocalization, as you're about to see, can really alter how these reactions proceed, specifically conjugated dienes. Okay? Isolated dienes are easy because they don't have delocalized electrons. Right? So if I take 1,5-hexadiene, which is an isolated diene, right? There's no delocalized electrons here, and I give it excess HBr, then it just does the reaction with each of the pi bonds exactly as we would predict from chapter 6. As we look at the mechanism, nothing here is brand new. You do it with one pi bond, and then you do it with the other pi bond. If you would have shown this one reacting first, that would be totally fine as well, because there's nothing new. You just do the reaction twice as long as there's an excess of this HBr. Okay. What if I have a stoichiometric equivalent, right? So I don't have an excess of HCl, meaning I have to choose one of these pi bonds to react with. Okay. Well, if they're identical, then you just pick one. But in this case, notice they're not identical. Okay. So if there's only one equivalent of my electrophile, it adds to the more reactive double bond. And the more reactive double bond is whatever produces the more stable carbocation. Okay. So in this case, right, the electrophile hydrogen goes to this carbon, and then I get a tertiary carbocation as an intermediate. Over here, hydrogen would have gone to this carbon, giving me a secondary carbocation intermediate. Okay. So because we know tertiary is more stable, that's why this pi bond reacts. Okay. And again, it's because there's only 1 molar equivalent of HCl. If there was an excess, then both of the pi bonds would react. But if there's only one, it's going to react with the pi bond that produces the more stable intermediate. Okay. Really a piece of cake for isolated dienes. Okay. Conjugated systems, when we have limited electrophiles, are where it gets a little tricky. So let's look at butadiene with 1 molar equivalent of Cl2 or 1 molar equivalent of HBr. Okay. Now notice in this case, because there is only 1 molar equivalent, only one of the alkenes is reacting, but it's giving us 2 products, which is kind of weird to think about. And these things are called the 1,2 addition product and the 1,4 addition product. I want to draw your attention to the fact that those numbers don't necessarily have to match up to the overall numbering scheme. They do in this case with butadiene, Okay, but even if we were working with a conjugated system in the middle of, octadiene, for example, we would still call them a 1,2 and a 1,4 addition. Okay, so let's see exactly what that means. When I identify the conjugated system, which remember we've talked about this in a previous video, you're looking for double bond, single bond, double bond. Then bam, you've got a conjugated system there. Number them 1, 2, 3, 4, and those numbers, right, refer to where the electrophile and the nucleophile from the addition reaction end up. If they're on adjacent carbons, that's the 1, 2 addition, right? And if they are on 1 and 4, right, that's the 1, 4 addition product with 2 carbons in between. Not too difficult, right, to see where those names come from. The big question, of course, is how? How do we get 2 products even though 1 alkene is reacting? So let's take a look at that. Okay. Well, with butadiene, right, it's easy because it's symmetrical. So I choose either one of my pi bonds to react first. Okay. So let's take the one on the left. Markovnikov tells me that this carbon gets the hydrogen electrophile, which gives me a secondary carbocation here. Okay. But that secondary carbocation is also, right, 1 sigma bond away from a pi bond right there. So that's also an allylic cation, which, as we've seen, is stable because it can be delocalized. Okay. So I can slide a pi bond over here, and that brings my carbocation over to this side. Okay. So these are 2 equal in energy resonance contributors. Okay. So now my bromine, my nucleophile, can add to this one, or it can add to this one, and that gives me 2 different products. In one situation, the hydrogen and the bromine added next to each other. That's the 1, 2 addition product. And the other one is the 1, 4 addition product. So the first step is always the addition of the electrophile to one of your alkenes. Then you get your carbocation, and you see the resonance contributors to that carbocation. But now the question becomes, well, what if it's not symmetrical? If I have something that's not symmetrical, right? Jumping back here, it was a toss-up. Butadiene, symmetrical, I could choose either one of those pi bonds to react with. But as we just saw with an isolated diene, where the pi bonds aren't the same, you protonate whichever pi bond to start gives you the more stable carbocation. So if we look at the possible carbocations, right, if I react with this pi bond, it gives me a tertiary carbocation. If I would have reacted with this pi bond, then it gives me a secondary carbocation. Right, and looking at the resonance contributors, this is a secondary in resonance with a primary, and over here, this is a tertiary in resonance with a primary. Okay, so of course, the one with the tertiary and the primary is favorable compared to the secondary and the primary. So that's going to control your product there, okay? I choose the pi bond. That's going to give me the more stable carbocation, tertiary in this case, and then I can make the 1, 2 addition product or the 1, 4 addition product, okay? But the products still aren't 50-50 because of 2 different possibilities. Right? It's not a perfect 50-50 split here between these products. And this is the challenging part of this video to understand. So make sure you're good with this concept. Make sure you're comfortable first with identifying the more stable carbocation and its resonance contributor so that you can predict the 1, 2 and the 1, 4 addition first. Okay? If you need some practice with that, pause the video now. Make sure you're understanding everything that's coming up to this point. Right, but then let's understand the fact that we're not getting a 50-50 split of 1, 2, and 1, 4. Okay? Because when a reaction produces more than one product, right, we have to see what kind of control it's under. Right? Because a reaction that produces what's called the kinetic product is said to be kinetically controlled. It's making whatever product is formed fastest. Right? Remember, kinetics is all about the speed of a reaction. So a kinetic product or a reaction that's under kinetic control makes whatever product we can form fastest. The flip side of that is a reaction we would say is thermodynamically controlled. It makes the thermodynamic product, which is the one that's more stable. Right? Because remember, thermodynamics is all about energy of reactions. So whatever is more stable is the thermodynamic product. Faster is the kinetic product, more stable is the thermodynamic product. And it is possible, as we'll see in a second here, for them to be the same thing. Right? The kinetic and the thermodynamic product could, in theory, be the same one. Right? They could be both preferred. But in order to understand that, we have to consider both the structure of the reactant and the product and the temperature of the reaction overall. So make sure you have those terms written down, you understand them, kinetic and thermodynamic product. And let's take a look for 1,3-butadiene. We've already seen the products that can be made here. The 1,2 addition or the 1,4 addition. So now what's the difference in these two? And this is where we have to think back to when we first started talking about alkenes, right? Why are they different? Well, if I run this at a cold temperature, then my kinetic product predominates. The 1,2 addition in this case is the kinetic product. So mild conditions or low temperature, right, which will be emphasized anytime you have a test. Right? And this is another key thing from chapter 8. You have to start paying attention to the conditions of reactions, because the temperature will alter the product you get here. Right? So if it's a very cold reaction, low temperature, that's always going to give you the kinetic product in a reaction. And when it's this cold, notice the arrow, the reaction's irreversible. It goes reactants to products and doesn't come back because there's not enough energy at that low of a temperature to overcome the activation energy going in reverse. But if I were to run the reaction at a higher temperature, now the reaction's reversible. Okay? So if you think about the energy barrier, right, for a reaction overall, I'll annotate this quickly. Right? You're going reactants to products. If it's too cold, then they can't overcome this energy barrier here. But at a sufficiently high temperature, right, then you can go reactants to products, and then you can go products back over this curve to reactants, et cetera, et cetera. And if that's the case, right, when we have a higher temperature, the reaction's reversible, then your major product is the thermodynamic product because it's more stable. And think to yourself, why is this alkene more stable than this alkene? I alluded to it just a slide ago, but what's the difference? Try and think to yourself. It's the fact that this one is more substituted. I have 2 alkyl groups on each side of this alkene versus only 1 over here. So this is the thermodynamic product. That makes sense. Why is that one more stable? Well, it's more substituted. So if we look at the energy diagram, the reaction coordinate diagram, well, it's the same first step, right? Notice there's no divergence there. It's my butadiene going to a common intermediate with 2 resonance contributors. Right? But then at the end of the day, the thermodynamic product, the more substituted alkene, is lower in energy than is the kinetic product. But also pay attention to the fact that the kinetic product here has a lower activation energy. Okay? So if it's a cold temperature, I don't have enough energy to get over this. Right? But so I can only get over this energy barrier to form the kinetic product. At a sufficiently high temperature, I can get over this energy barrier and form the thermodynamic product. And this is a key idea, even if I form the kinetic product first, at a sufficiently high temperature, then you can overcome this energy barrier backwards and then form the thermodynamic product again. And then when you're forming the most stable one, you're done. And that's key to the understanding for the thermodynamic products, right? They have that common intermediate. Yep. Both products come from the same intermediate, so they can interconvert at sufficiently high temperature, right? Kinetic can go back, and then it's a 50-50 shot. Right? Might become kinetic again, but eventually it's going to become the thermodynamic product. But the thermodynamic product doesn't go back as easily. Okay. So that's key. That's why temperature is key. Low temperature, right, you can only get over that barrier and then you stay there. Okay. High temperature, you can get over any energy barrier, right, including going back from kinetic to thermodynamic. And then when you end at thermodynamic, you're done. So that's why thermodynamic predominates. Tricky stuff. Right? Make sure if this doesn't make sense, you can review it in the textbook or we can talk about it face to face. But it's also summarized nicely in these two slides, 95 and 96. If a reaction's under kinetic control, right, both reactions are irreversible. You just go one way. It's too cold. You don't have enough energy to go back. Right? So A goes to B or A goes to C, and then you just stop. Whichever one's formed faster, that's the one that predominates. Depends only on the reaction rates. If a reaction is under thermodynamic control, right, reactions are reversible, at least in one way, if not both ways. Right? Note the difference in the arrows. So because you can always interconvert, right, it's whichever one is more stable at the end of the day. If there's enough energy to get back to the intermediate, and stability is significant, and more of the thermodynamic product is formed with time. Yep. So something that's irreversible under the conditions that are employed is kinetically controlled. And the key thing that you're looking for at this stage of the game is low temperature. You see a low temperature, okay, specifically something in the negatives, right, that's going to be kinetically controlled. But when you're at higher temperatures and you have sufficient energy available to make one or more of the reactions reversible, then you can bounce back and forth the reactions under thermodynamic control. Eventually, you're going to form that more stable thermodynamic product. And every reaction has a temperature where it switches. It depends on the reaction to get the specific temperature, but certain temperatures will be kinetic control, others will be thermodynamic control, which is why in the test, I'll make it very clear if these things are running cold at kinetic control or running hot under thermodynamic control. So we already talked about this, right? Why is the thermodynamic product more stable? Well, it's the more substituted alkene. Right? That should make sense from chapter 5. But what we haven't addressed is why is the 1,2 addition the kinetic product? Why is that formed faster? Well, let's see why that is. Okay? Well, it's not a transition state argument, which is usually what we're considering in the world of kinetics, right? Talk about the transition state. A more stable transition state is lower in energy, so it's easier to overcome the activation energy, reach the transition state, form the product faster. 9 times out of 10, that's what kinetics is all about. But that's actually not the case here. Right? Because if we look at the transition state for the 1,2 addition, right, and the transition state for the 1,4 addition, then if that were the case, we'd form equal amounts of 1,2 and 1,4. And it's not the fact that the kinetic transition state more closely represents the 1,2 contributor. It's actually much easier than that. It's just called the proximity effect, which is super simple. Why is the kinetic product the kinetic product? It's simply because it's closer. If we think about the pi bond, right, after I add, this is working with BCl, right? So you can add deuterium and track where it goes. Right? In this case, I added my electrophile and then my nucleophile comes here just because it's closer. Right? Proximity effect caused by one species being close to another. Right? And that's been proven because the 1,2 addition product, as you can see, predominates at cold temperature, tracking it. Still 2 resonance contributors, right? But the 1,2 addition is formed faster because of the proximity effect. Make sure you have that jotted down as well. Why is the kinetic product the kinetic product? Because of the proximity effect, the 1,2 being closer together. So once you have these things understood, what you'll need to be able to do is look at a conjugated diene and predict the kinetic and the thermodynamic products, keeping in mind that sometimes they're the same. You could be asked to do this for an isolated diene as well. Those are easier. Right? We only spent a slide or two on that at the beginning of this video. Right? But if you're given a conjugated diene, it's a little more challenging predicting the kinetic and the thermodynamic product, especially if they're not symmetrical, which is not the case here. So let's think to ourselves, okay, well, I've got something that's not symmetrical in this case. So what am I going to make? Which pi bond am I going to target? Okay. Well, you shouldn't assume, right? We just discussed the fact that the 1,2 product is always the kinetic product, but don't assume that the 1,4 is always the thermodynamic product, right? Because we need to think about the structure overall of the conjugated diene, and if it's possible to make it more substituted. Okay? Because if I attack this pi bond right here, then I actually get rid of the most stable alkene, right? Because look at this alkene, it's 1, 2, and then 3 alkyl groups. That's a pretty stable alkene. Okay? So rather, I'm going to attack this pi bond over here. 1, 2 is always the kinetic product, so that's easy, right? Put the hydrogen here and then the bromine over here. But it's also the thermodynamic product because it preserves the more stable double bond. If I do the 1,4 addition, then all of a sudden that alkene only has 2 alkyl groups. So you always have to consider the alkene stability. Hopefully that makes sense. Look at the structure overall. Preserve the most stable alkene. Sometimes that alkene, right, it happened with butadiene, will move to the middle and that'll be more stable. But I went from 3 alkyl groups to 2, that's no more stable. So in this case, the 1,2 addition is both the kinetic and the thermodynamic product. How about another example over here, right, with a conjugated diene and hexadiene? Okay, well, I take that plus HCl. I know 1,2 is going to be my kinetic product, but how about a thermodynamic product? Well, in this case, I have an alkene with 2 alkyl groups. And in this case, 1,4, I have an alkene with 2 alkyl groups. So in that case, there is no thermodynamic product because everything is of equal stability in terms of the final energy. So if there's no thermodynamic product, which one's going to predominate in the reaction? Whatever the kinetic product was, okay? Because there's nothing that's favored thermodynamically. Doesn't matter what temperature this one's run at, okay? This product is going to predominate. However, and then jumping back to this one, right? Kinetic and thermodynamic product are the same one. So this one will predominate. And I'm going backwards in slides again. Something else, let me find the slide I'm looking for. A reaction like this, where the kinetic and the thermodynamic are different, cold temperature favors the kinetic product. Warm temperature favors the thermodynamic product when they're different. When they're the same, that's easy. Doesn't matter the temperature, it's favored. That's what we had on this slide. And if there is no thermodynamic product, then the temperature doesn't matter. You're always going to favor the kinetic. So the key takeaways from this video, right? Hopefully you saw the fact that isolated dienes are a lot easier. Now look at a conjugated diene, consider the alkene stability, find the thermodynamic product if there is one. 1,2 addition is always the kinetic product, and then consider the temperature of the reaction. That's going to help you predict the products of the reactions of conjugated dienes, which will be a point of emphasis for exam 4.